Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone, and welcome back to AI for Good, AI for Climate Science. My name is Philip Stier, and I'm the host today, together with Duncan Watson-Paris. So we're back after a little bit of a break, where we decided to slow down a little bit, but now the program of this Climate Science series is picking up again. And so we're really delighted to have Elizabeth Barnes with us today as a speaker, who will nicely kick us off again for more talks on that topic. So Elizabeth has undergraduate degrees in maths and physics, and then did a PhD in atmospheric science in Washington. Then did a one-year postdoc with NOAA in the Lamont Observatory, and then joined the Colorado State University faculty, first as an assistant professor, now she's an associate professor. She has a really broad and deep background on particularly focusing on climate variability. And in the more recent years has really thrown a lot of AI and modern data science tools at understanding variability and change in the climate system. I won't embarrass her with a shockingly long list of awards she has on her webpage. I just mentioned she most recently has been awarded the McElwain Medal of the American Geophysical Union. That also then came with her being elected as a fellow of the American Geophysical Union. But today, Elizabeth will talk about exploring anthropogenic change through an AI lens. And focus is really how explainable AI can help to visualize change in the Earth system over time. A very timely and interesting topic. And over to you, Elizabeth.
Thank you, Philip. Let me get my slides up here. How do we look? Look okay?
Yep, very good.
All right, thank you everybody for joining. I'm really excited to be here. As I think will become apparent, love talking about this topic so much. So let's get into it. So in climate science, we have so many tools that we use. We use physical equations, that is, physics and math. We have dynamical climate models where the physics is sort of embedded in that Earth system model, but we also have more simple, basic statistical tools like many other fields. For example, one of my favorites is linear regression. If you want to know that the world's getting warmer or say temperatures are going up, fitting a line can do the trick. We also have slightly more advanced statistical methods in there, like principal component analysis, etc. Here, I don't mean to suggest in any way that those tools are leaving our toolbox. Instead, the way I see it is machine learning, or AI, is really just one additional tool in that toolbox that we can use to understand the human Earth system and the dynamics between it. So in my group, our focus is generally on the idea of taking information from the Earth system, processing it through machine learning algorithms, and outputting useful, or hopefully useful, predictions about the world around us. So I know this is AI for Good, so everybody here probably maybe knows a little bit about machine learning and AI, but my framing as a scientist, as a climate scientist here, is that part of our job is to sift through piles of data and try to extract useful relationships that apply elsewhere. Now, as a scientist, I would call that learning physics of the climate system, but this concept is really that of out-of-sample predictions. We want to learn something from our data that applies to data we haven't seen before. And in essence, this is what many machine learning methods exactly are designed to do. Whether they do it well or not is the big question. So machine learning for climate science has actually been around for quite a while now. Here are some earlier papers. For example, there's a pretty a pretty awesome paper from 1964. And if you look in that bottom right-hand corner, you'll see there's a tiny little schematic. And if you look closely, it looks a lot like an artificial neural network. And indeed, that is what this author is using to make meteorological predictions back in the 60s. Now, there are lots of more recent examples of machine learning generally for climate science. And before I get into a few of the specifics, I want to talk about some of my favorites. So this is an example that came out a few years ago, and a colleague saw this NVIDIA video on YouTube where they showed how they could infill an erased part of an image, in this case, an image of a woman. And they erase the eye, and they show how they've trained AI to replace that eye and put it back. Now, if you look carefully, you'll see first that the eye's in the right spot, but the makeup's wrong. So again, these algorithms aren't perfect, but at least in this case, it was able to infill the right feature in the right spot. Well, these authors, these climate scientists saw this and said, well, this looks a lot like temperature reconstruction. So in the 1800s, we actually have quite a bit of observations, as shown on the left, from ship tracks and people on land taking measurements, but there's a lot of, for example, open ocean that's missing. So Cato et al. Used this NVIDIA algorithm to actually replace or infill the temperatures where they were missing. And while there are many methods already in climate science to do this infilling, what made this particular AI method special or noteworthy was that they knew that from written reports that in 1877, there was a very strong El Nino Southern Oscillation, a kind of climate pattern that occurred based on written records of what was going on with rainfall patterns over South America. But most infilling techniques actually were not able to reproduce this event. And this particular AI method was. Now, that's just one example. What I love about this example is the idea of taking tools from other fields, in this case, the commercial sector, and bringing them to do climate science. I have so much fun with this. So there are other applications. For example, in the climate community, we're using AI to do extreme event detection. Say, instead of detecting cats and dogs in an image, let's detect tropical cyclones or atmospheric rivers. We're using it for weather prediction. Some colleagues have actually trained a fully AI-driven weather prediction model where the forecast is shown here on the right and the truth is shown on the left. And you can see it's actually doing a reasonable job. Another example for climate science, it's a big area, a big push right now in our field, is trying to improve our climate models, specifically cloud processes and how they are simulated in climate models. We know that there are a lot of issues with what are called convective parameterizations, or the equations that we use in our climate models, and there are many colleagues trying to use AI to improve these algorithms. Another favorite of mine is the concept of equation discovery with AI. A lot of people sometimes think, especially in the geoscience community, they think that equations and AI are somehow at odds with each other, that they're sort of opposites. But in fact, colleagues are using AI methods, data-driven methods, to discover or find those underlying physical dynamical equations, in this case of ocean eddies. And finally, an application that I think is going to have huge promise moving forward is the idea of using AI for climate change communication. In this case, there's a group out of Canada, Mila here, who's using AI to take a picture, say, of your house and actually show you what it might look like if under inundation. And in this way, communicating the potential impacts of climate change on exactly where you live, allowing people to really visualize what that means for them. Now, I tell you about all these examples because we're not going to talk about any more of these today, or I'm going to talk a bit more about the work that me and my group have been doing. And before I get there, I want to show all of these faces to recognize that it's not just me sitting here doing all of this work, but it's really a team here in my group at Colorado State that are working together, early career scientists working with more senior scientists to explore the use of AI for climate science and discovery. So just taking a broad view, to me, what are some reasons that I want to use AI for my science? Well, one of the reasons is just to do something better. I already mentioned that our ability to simulate clouds and climate models is still not perfect. And we're using, and the climate scientists are using AI to try and make them more accurate. However, another reason one might want to use AI for climate science is to do something faster or cheaper. An example of this is we actually know the physics of the radiation quite well and have the equations to put into our climate model simulations. However, this part of the code is exceptionally slow, the bottleneck, if you will, in running these simulations. And people are working on using AI methods to speed things up. And finally, where my group really comes in is, to me, this third point, which is that we can use machine learning and AI as an additional tool to learn something new about the climate system. That is, we can discover nonlinear relationships we didn't know were there, even in the case where this method may be slower or may even be a little bit worse than something else. Maybe we can learn something new in the meantime. So I'm going to talk about two applications of how we're using these tools in my group. And the first is focused on the concept of detecting force change, or detecting climate change in the Earth system and its impacts. Now, finding force signals is a challenge in the presence of climate noise. And so the idea is to use AI to try to circumvent that at least a little bit. All right, so when I talk about force change or climate change, let's all get on the same page here. This is a picture of temperature changes from the end of the 21st century compared to 1850 to 1900, so sort of a pre-industrial era. The redder regions mean a larger increase in temperatures, and this picture is made from many climate model simulations under an extreme warming scenario. Now let's step back and let's talk about big picture. What do we see? Well, first of all, we see it's red everywhere. What does that mean? It means that the climate is warming on average across all of these models over these two sets of time periods. The second thing you'll note is that the continents the land looks a little bit redder than the oceans. And this is a well-known feature of climate change where the land surface warms faster than the oceans. And finally, sort of the elephant in the room here is the Arctic. You'll see the Arctic is warming much faster than the rest of the globe. And this is known as Arctic amplification and is a well-known fingerprint of human-induced climate change. So what's so hard about this? This pattern looks so obvious. Why is it difficult to detect change? Well, hidden in this very clean picture is the fact that I have averaged over multiple decades, and I've averaged over many climate models. And all of that averaging has helped reduce the noise. That is, the noise from internal climate variability. That is, 1 year doesn't look like the next just from the noise of the climate system. But I've also averaged out the fact that climate models often have disagreement with one another. And that's all been averaged out into this one plot. Well, that's all good and fine, except when we make a picture of what the observations, what our real world is doing, it raises the question, how can we tell which changes our signal and which are noise in our one observed Earth, where we can't average out everything and get that clean warming pattern? If we were able to answer this question of dividing the signal out from the noise, that raises new questions. For example, what are the patterns of change that we've seen over recent decades, and what might we expect in the future? What's the timing of this detection? When can we detect certain patterns of forest change and where? And finally, thinking about our climate models themselves, which climate models and do climate models simulate these changes correctly? And how can we go about answering that question given that we only have our one observed Earth? Now, there are many, many people who for decades have been asking these same questions. I do not want to imply in any way that we are the first to ask these. What I'm going to tell you today instead is about how we're using explainable AI to try and attack these questions in a slightly new way. Now, specifically, I'm going to set up a problem that's going to sound a bit silly at first, and hopefully by the end, I'll convince you that it was worthwhile. So what are we going to do? We are going to take many maps of temperature from many different climate models. So annual mean surface temperature maps, and input them into a neural network and task the network to predict what year that particular map came from. So every climate model is simulating the climate system from, for example, 1850 to 2100. We take 1 year from that simulation and make a map of annual mean temperatures. We feed it into the neural network and we say, what year is it? So you can imagine, think of the year you were born. There's a map of temperature for that year from every climate model. And we want the network to learn to identify what year that is. Now, before I tell you how it did, I actually find it's really useful to first test this concept on data that I know will be unsuccessful, that I know won't work. Specifically, what we did is we took a control simulation that is, it's just a climate model running with constant 1850 forcing, if you will, no trend in anthropogenic climate change. Now, because variations from map to map are only due to internal climate variability, there are going to be no indicators of what year it is, because every year is like every other year, just with a little bit of noise. And you can see that on the left-hand plot, where I'm showing the actual year of the map on the x-axis and the predicted year on the y. So the one-to-one line is that diagonal. So that's a perfect prediction. And while my training data falls nicely along to that one-to-one line, making it look like, hey, this neural network can do this problem, the black dots are my out of sample or my testing data. And you'll see there's absolutely no rhyme or reason to those predictions. They're all over the place. Now, this is a textbook case of severe overfitting by the neural network, but the point here is there's nothing to learn from one map to the other, and so the neural network fails in this task. Now, what happens when we feed it data from our climate model simulations that are run from 1850 to 2100? That is where there are patterns of forced change. When we do that, in order to be successful, the neural network has to learn regional signals that are reliable indicators of the year. So how does it do? Well, short answer is it does pretty well, or I probably wouldn't be here talking about it. So here's what we're looking at. The gray dots are the training climate models or the training data, which you can't really see because they're hiding under the colors. And the colored dots are our testing data or out of sample data. Once again, the actual years on the x-axis and the predicted years on the y-axis. So a perfect prediction would fall along that diagonal. So you can see after about 1970 or so, the neural network is doing quite a good job at predicting the year from given temperature maps. But what's a little strange at first, maybe, is that prior to about 1970, the neural network is doing a terrible job. It just predicts about 1950 all the time. And when my computer science colleague saw this, he came to me and said, I don't know what's wrong with my training algorithm. It's just not working. And this is one of those cases where I think it's so important and exciting to have physical scientists working with the computer science community, because I was able to say, well, wait, no, this has nothing to do with your neural network. This is physics right here. What this is telling us is that until about 1960 or 1970, there was no reliable indicator pattern that the AI could identify. And it wasn't until about the 60s or 70s that the neural network was said, oh, I see a pattern. I see force change. You know, I'm detecting force change and I now know the year. And from then on does a good job. All right, so the neat thing is up until now, we've only trained this neural network with climate model data. What about the real world? Well, once trained, we can freeze the weights and biases. And what we have is just a prediction model now. And what we can do is push through any maps of temperature, no matter where they come from. So in this case, we now push observed temperature maps through our trained neural network. And the results are shown by the white circles. So a few points. One thing I love about this application is that no one's going to argue with me what year it was and for the observations. And we know what year it was every time we took data. So we can really assess how did the neural network do. And hopefully you'll agree with me that those white dots largely follow along that diagonal. That is, the neural network has learned useful information from the climate models to identify force change that are also applicable to the real world because of its ability to predict the year from observations. All right, so at this point, you may be thinking, what did I sign up here for? This person's predicting the year. This seems pretty silly. You know, I have two small children and both of them know the year's 2022. Why would anyone want to predict the year? Well, this is where I said it seemed a little odd at first, but my goal actually is not to predict the year because there isn't really much use in that. Instead, what if we could learn which regions were most relevant to predicting the year? Then we could start to identify those patterns in the climate system that allowed the network to know what year it was and potentially identify force change. Now, to do this, though, we have to get rid of this concept of the neural network being a black box. Instead, what we're going to do is leverage advances in explainable AI to try and understand the decision-making process of the neural network to thus extract information about the climate system. Now, there are so many papers out there already in the computer science community about opening the black box with explainable AI. However, geoscience communities are just starting to catch on. And in the past few years, there have now been multiple papers, some of which were done by people in my group, trying to demonstrate the use of explainable AI for geoscience applications. And I think this is incredibly important, trying to bring the information, again, from the commercial sector or the computer science community into climate science. Now, we've messed around and used quite a few of these XAI methods, but I want to tell you a little bit about attribution methods and how we're using those in our group. So attribution heat maps, largely we have found to be very useful because they're consistent with how we as climate scientists tend to pose our questions. What do I mean by an attribution heat map? Well, here's an example from some of the developers of a particular attribution explainability method called layer-wise relevance propagation. Specifically, let's say you've trained a network to predict the probability there's a cat in an image. So once trained, you can push a new image through and ask the network, what's the probability there's a cat? And it might point out that it's 0.8, so 80%. You say, very interesting. Okay, but why? Why did you think there was a cat in the image? Well, we can use explainability methods to go back through the network and to propagate this 0.8 back through the network to create a heat map or an attribution heat map of the most relevant regions for the network's predictions. Now you can see that here in the gray with the gray image, you'll see the reddest regions are around the region of the cat, meaning that the network used the parts of the image where there's a cat to know that there was a cat. So this may be a little underwhelming, but you get the gist of how this is working. All right, let's go to a few other examples. Why would we use these methods in general? Well, one reason to use explainability methods is to help identify problematic strategies of your AI system. So this is a great paper. I highly recommend it, called Unmasking Clever Hans. And let me just walk you through a really great example where they've tasked the network to predict whether there's a horse in the image this time. Now, the network does a great job and indeed it identifies that there are horses in both of these images. And then we can use explainable AI to ask, how did the network come to its conclusion? And if you focus on the red regions here, these heat maps, you can sort of squint and tilt your head and maybe convince yourself that the network is looking where there's a horse to know and make its prediction that there's a horse in the image. Okay, fine. Let's go to another example of some horses. 3 more horse images, and the network once again correctly identified that there were horses in all 3 of these images. So we can once again make heat maps and ask what were the most relevant regions for the network's prediction. Now, in this case, the brightest colors, those yellows, are not actually where there are horses. The network is using the bottom left-hand corner or relying on it for its decision-making process. And we see that actually it's not looking at horses, it's looking at the copyright symbol in the bottom left-hand corner. That is, the network was trained on many images of horses that came from the same German website and has learned to use the copyright symbol as an indicator of whether there's a horse. Now, on the one hand, you might say, well, it got it right. There was a horse in the image. But on the other hand, again, as climate scientists, we see this and this makes us nervous because ultimately we want to be getting the right answers for the right reasons to try to better understand why the climate system is doing what it's doing. So in this way, explainable AI techniques allow us to start to identify these problematic strategies when they're present. So again, as climate scientists, our ultimate goal is typically to understand why. But sometimes I get some pushback and people say, well, I don't care about why, I just want a good prediction. And there are still reasons you should care about explainable AI as a tool. One, for the reason I already mentioned, is to gauge trust in your network, that it's getting the right answers for the right reasons. Another reason that we use explainable AI is to fine-tune and optimize our networks. So especially when our networks are not doing a good job on problems we thought it should, we're able to use explainable AI to go back and identify the decision-making process and maybe slightly transform either our inputs, our outputs, or our architecture as informed by our knowledge of the system to optimize our network. And finally, I alluded to this earlier, but explainable AI allows us to go back and probe the decision-making process and thus potentially learn new science. So this brings us back to our example of predicting the year. I mentioned it was pretty silly just to predict the year, but what if we could identify the patterns the network used to predict the year? That is, which regions are relevant for this prediction? So we use explainable AI techniques. In this case, we use layer-wise relevance propagation to propagate that prediction back and ultimately create a heat map, which in our case is a literal map of the globe, where the darker regions show us the more relevant regions for the network's correct prediction of the year. So for example, we can make such a heat map for predictions of the year 2015. And you'll see that there are absolutely regional indicators that the network is using. For example, it's using the North Atlantic, as well as the Southern Ocean, and Southeast Asia are all regions that are incredibly relevant for a correct 2015 prediction. Now you can do this for more than just the year 2015. You can do it for many different years. And the idea is because neural networks allow for nonlinear relationships to be learned, as well as multiple pathways, the neural network can create a different or identify different relevant regions of forced change depending on the year. So in this case, you see 2015, 2035, 2075, and 2095 all have distinct patterns that the network is using to identify what year it is and thus force change in that particular time period. Now, before I move on, I want to point out that if you're actually looking for the response of the globe to anthropogenic climate change, that was that first picture I showed you at the beginning of this talk. Anthropogenic climate change is causing the globe to warm everywhere. Instead, these maps are not that. These maps should be thought of as indicator patterns of forced change. That is, they are a combination, or indicator patterns of a changing climate, and they're a combination of signal, the strength of that temperature warming, and the climate noise there. So if you will, it's a signal to noise ratio, as well as incorporating model agreement on climate model agreement on what that change and signal and noise should be. All right, so a few other things to point out on these maps. First of all, you'll see in 2015, the Southeast Asia sign, and we think this is the network picking up the temperature response to anthropogenic aerosols emitted in these simulations over this region and time period. Another thing that is interesting in looking at these is, and this is a terrible map projection for this, but you're going to have to trust me that the Arctic has almost no relevant signal. That is, the network really isn't using Arctic information to make its prediction. And this may seem counterintuitive because I already mentioned that Arctic amplification, or the fact that the Arctic is warming faster than the rest of the globe, is a major fingerprint of human-induced climate change. So what's going on? Well, once again, the idea here is that the network is looking for good indicator patterns. And while the Arctic is getting warmer faster than the rest of the globe, the Arctic also has some of the highest amounts of climate noise in the entire climate system. So if you will, the signal to noise ratio is actually relatively small. And in addition, climate models often disagree on the timing of warming in the Arctic. That, for example, when Arctic ice will fully melt. And because of this, the neural network has identified that, or has decided that this is not a good indicator, and it will look elsewhere for its reliable indicators of a changing climate. Well, so far I've shown you how we're using explainable AI to understand the network's decision-making process with climate models, but what about observations? Well, we can do the same thing with observations. For example, the top map shows observed temperature anomalies from the year 1997. And I chose 1997 because this was a very strong El Nino year. You can see very warm waters off the coast of South America there, indicating that strong El Nino, which is just an internal climate variability mode. So when we push this map through the network, this is not cherry picked, it just so happens the network says that the year is 1997. So it gets it exactly right, which is pretty phenomenal in my view. All right, but then you can ask the question, well, how did the network know that it was 1997 in the observed map, with the observed map? And that's what the bottom panel shows you. The bottom panel shows you that heat map, that explainable AI heat map of the most relevant regions. And what you see is just because the coast of South America was showing very warm air and water from El Nino, the network is not using that region to make its prediction because this is internal climate noise and it's learned to ignore that. What it's looking for is forced change. Instead, the network puts a lot of relevance, it appears, off the coast of southern Africa, as well as the Southern Ocean, as its most relevant regions for the network's prediction. One other thing we can do, the fact that now we've trained an AI to predict the year and used explainable AI, is we can use more advanced neural network techniques, in this case, something called backward optimization, to understand differences between climate models and the real world. Specifically, we want to look at regional effects, and so we remove the global mean temperature from every map. So the neural network can only learn relationships between regions in order to predict the year, and can't rely on the steady trend that every map sees. In this case, our network actually ends up being quite wrong on the observations, and it thinks that the observations are about 20 to 30 years later than they actually are. The reason for this bias must then be because our climate models also have errors in how they're simulating these regional relationships compared to the real world. And we can use backward optimization to ask the question of where is the network going wrong from learning from climate models. And what we end up finding is this bottom panel, which shows that the models are too cold over the land compared to the ocean in these reliable regions, and that the models are too warm over the North Atlantic warming hole. So I realize this is a bit in the weeds, but this is where I think a lot of these AI tools can start to be used, is in model evaluation and understanding where is it really important to get things right if we have to start to put our resources towards certain model development projects. All right, so that example is really about leveraging imperfect climate models to better constrain future projections by fusing simulations and observations together with explainable AI. In my group, we're also exploring Earth system predictability weeks to years in advance to study prediction, dynamics, and change. And this is on even short timescales like subseasonal to seasonal timescales, or predictions from, say, 2 weeks to 2 months. But we're also using explainable AI to do decadal predictability. That is, start to prepare, produce products to start to prepare society for the next, say, 2 to 10 years. What might we expect? Now, I want to talk a little bit about that, specifically the concept that predicting what's going to happen in the next 2 to 10 years is a really hard problem. Beyond the weather timescale, we must look to specific states of the Earth system or opportunities that lead to enhanced predictable behavior. And that's because chaos, the atmosphere and climate system, is incredibly chaotic. And so in this sense, I don't think we can ever really expect to make perfect predictions all the time. And this is where I think AI can really shine, helping us identify these opportunities for successful predictions when they occur. Specifically in my group, we're leveraging AI to identify and explore these climate states that lead to more predictable behavior than others. So I'd like to tell you about a few examples of how we're thinking about this right now, but I think it's applicable to more than just decadal predictability of the climate system. I actually think this is incredibly applicable across science questions. So in this work, my former graduate student, Benjamin Toms, trained a neural network to take maps of sea surface temperature and predict the average land surface temperature 5 years into the future, say at a particular location. So these are examples of, once trained, he can use explainable AI to look back through the network and ask what regions of the ocean's surface were most relevant to correctly predicting the temperature over at some other location years in advance. And if you can see the screen, you might be able to see in each of these panels is a little red dot. And that is the region we're making predictions for. So that's our predict and. And we see that depending on where that dot is, where we're making predictions, we have different sources of predictability identified by the neural network, as shown by the bright colors in these XAI relevance maps. But even if we focus in on one particular region, in this case along the US West Coast, one of the strengths of using AI for this problem is that it can identify nonlinear and different pathways that lead to predictable behavior. In this case, we see there are 3 different sources of predictability that the network's identified for the same region. That is, we may get predictable information of the temperature years in advance along the US West Coast, either from the Western Pacific along that Kuroshio extension, or over the North Atlantic, which will also hold information for predictable behavior. And then finally, looking at sea surface temperatures right along the West Coast can also provide information, unique information about what temperatures may look like in the coming years. Taking this a little bit further, we've been exploring how, again, can we identify the state-dependent predictability? And my graduate student, Emily Gordon, has been actually using a neural network to predict probabilistic distributions to quantify uncertainty and identify more predictable states. In this case, she's inputting ocean heat content, so a measure of how much heat is stored in the ocean, in an attempt to predict the sea surface temperatures, again, about 5 years in advance, in this case over the North Atlantic. Now, the network in this case predicts not only a mean, but also a standard deviation that is an uncertainty for how confident it is in its prediction. Thus, every prediction that this network makes is really, in this case, a Gaussian, where a narrower Gaussian implies that the network is more confident in the predictions that it's making, and a wider Gaussian means it's less confident. Now, this on its own can be incredibly useful, having uncertainty information about the network's prediction. But we can take this further to once again try and better understand the climate system. So what Emily has done is she's identified that the most certain predictions by this network actually end up being positive predictions. That is, positive sea surface temperatures over the North Atlantic. And indeed, the positive predictions are in fact more accurate as well. This is exactly what I'm talking about when I talk about state-dependent predictability. It turns out that these predictions over the North Atlantic appear to be more easily predicted when they are of a certain sign. This is true over much of the North Atlantic. So the yellow plot here, the yellow color showing the 20% most confident predictions often occur over the North Atlantic. And we find that it's what appears to be happening is that the network is identifying the transport of positive heat anomalies into the region years ahead. Now, this is just focusing on the North Atlantic, but I want to point out when we think about state-dependent predictability of land temperature, this is true over the globe. So on the left-hand side is maybe what the accuracy you would get for a particular problem if you looked at all predictions the network makes. But on the right-hand side, when you take only the most confident predictions by the network, that is where its state dependency implies that it is confident, you see that that accuracy is much, much larger, suggesting that we should really be taking advantage of the network's uncertainty and knowing when to trust that prediction or when that prediction might actually be right versus not. All right, so what's next? I want to end with a few big ideas and one application, one more application in this case to the Sustainable Development Goals. First, I will say as a climate community and as an earth science community, I don't think everyone's quite yet on board to fully embracing data science as a part of our field. And this is something I'm very passionate about. Our field is creating data faster than we can process. The data is sitting there, but nobody's looking at it. And I think AI offers a tool to identify patterns in relationships, to extract information and build new knowledge from all of this data at a speed that might allow us to keep up with everything that's being made. Next, the concept of knowledge-guided machine learning, or we need to continue to fuse scientific knowledge with AI for climate science. In my view, the future of climate science is not one of data-driven methods taking over. Instead, to make substantial progress, we have to continue to fuse these two ideas together. You know, why throw out the hundreds of years of amazing physics that we've discovered already just to use AI? I think there's so much to be done combining the two. And there are many colleagues actually doing things like incorporating energy conservation or mass conservation into their AI algorithms. In my group, I think of incorporating knowledge is how we set up the problem, the question we're asking, and how we use explainability methods in the entire process to bring in old knowledge and extract new knowledge. In the climate community, there's a huge push I already mentioned to improve climate predictions and projections, and that a lot of AI is already being used for the building of climate models, but I also think there's a lot to be done for the evaluation of climate model output, the evaluation of climate models and the use of climate model output. I think these are early days. And finally, I think we need to continue to increase our focus. And I know this is a big focus of this group, which is so exciting, but to continue to increase our focus on using AI for human Earth system interactions. For example, quantifying the present and predicting the future transformations of the Earth system by humanity. And so I want to end with one application that we've used AI, explainable AI, to do this, specifically on mapping the human pressures on the landscape. Now, why would we want to create a near present metric of how much humans are impacting the land surface? And there are so many people I know working on land use change and AI. Well, specifically, we're just looking at the human pressures on the landscape. Mapping these effects on the land surface at a global scale is a significant undertaking, and current efforts tend to lag the present day by about 5 years. This is an issue because development can take place very quickly, with extensive change happening in a matter of years, not decades, and some changes may be irreversible. And so up-to-date metrics can provide a complementary method for predicting and tracking change. Now, there are already many methods and metrics for land use change and using AI to do that. But this is one example of a human footprint index, specifically a value often used by like ecosystem community, a value from 0 to 1, where 0 is pristine landscape and those bright or purples, and a 1, you can imagine something like a big cement parking lot or something. So humans have really changed that land surface. And that's shown here in yellow. Now, this particular group, the Williams et al., used and ingested data from built environments, population density, nighttime lights, etc., to put together this particular human footprint index. However, this took many years to do, and it's a lot of work. And so what my colleagues and I did is we decided to try and replicate this effort, but using AI to ingest Landsat imagery and identify the human footprint index from this Landsat imagery alone. That is, we take in pixel maps or little pictures of the land surface, we process it through a convolutional neural network, and we output a prediction between 0 and 1 of that human footprint index. Now, we can recreate a map of the human footprint index for the year 2000, as shown here, and it looks quite similar to the one that already existed. But we're then able to update it in near real time as Landsat imagery continues to come out. And so we can make a map of the 2019 human footprint index in a matter of minutes. And I can flip back and forth, and you can see large changes occurring across the globe where, for example, humans have begun or have continued to have a larger footprint on that region. Now, if we actually take the difference, we can make a map of changes in the human footprint index identified by our AI between 2000 and 2019. There are lots of interesting regions to look at, but we've highlighted 6 here. Where the left-hand plot is, or the left-hand panel is what the Landsat imagery looked like in the year 2000. The middle panel is what the Landsat imagery looked like in 2019. And the right-hand panel, in this case, is that XAI, or that relevance heat map, showing the regions that the network looked for its prediction. And we do this to gauge trust in our network. And once again, hope and ensure and check that the AI is learning the right relationships for the right reasons. And you'll see, for example, over the wind farm installation over Texas in the United States, the network is indeed identifying the roads that have been made to get out to the different wind farm installations. Or the deforestation in Brazil, once again, the network is identifying the roadways and the particular cutting structure to identify that this is human-induced changes in forest cover rather than something more natural. So to wrap up here, to me, the future of climate science is going to become even more broad than it is already. And it's going to really require the mixing of knowledge from many different fields. This is something I think that machine learning and AI is incredibly good at. Ultimately, however, we want to know more than just a prediction. We want to know why. And that is a big, I think, message from many scientists across the globe. Even if it's a great prediction, we still are in the business of understanding why. And so because of this, I think explainable AI is going to be truly transformational for the future of climate and sustainability research. And with that, I thank you.
Fantastic.
Thanks so much for a really, really fascinating talk. This was really good. But I'll hand over to Duncan for the questions.
Yeah, no, there was some really, really interesting work, some of which I'd heard of, and some of which was new to me. So that was really, really great. The work you just described actually on the land usage change was really interesting, and I wondered, with that time series now that you can do with kind of powered by AI, have you got ideas about how you might leverage that to understand, for example, what impact that has on flood risk or other kind of climate impacts, right, which are mediated by the changing atmospheric conditions, but also obviously have a component due to land change?
Yes, I think that's my short answer. Yes, we haven't actually done this, but this is the next step. I mean, this is a really exciting data set. So this human footprint index has long been used in the ecosystem ecological community already. What we're providing is not a new data set. It's new in the sense that the most recent was actually from 2012, and now we have 2019, and actually the 2021 Landsat imagery just came out, so we could presumably make one for just last year. So I think that's the new push here. I think we're really interested in this time series, however, to also try to explore changes in how humans are actually impacting the land surface and developing, and see if we can actually learn from that with using these explainable AI methods. However, we haven't done it yet. We're just excited to do it. So yes, coming up. Yes.
Excellent.
Maybe I'll come in with a question here. So you touched on sort of the human, sort of the detection and attribution problem. At some point you pointed out that that is most likely error source, but the tricky bit is obviously in the classical detection attribution problems, we tend to use sort of control runs of climate models and with the individual forces on and off. Having worked a bit on the aerosols and the pattern change, the problem is often that even though the forcing patterns of aerosols and greenhouse gases might be totally different, they project on the same modes of variability and often give it the same spatial pattern, strangely. Do you see any potential to still advance the attribution problem there? Sort of in particular, I'm thinking less of temperature, but also precipitation.
Yes, great question. And we have done this for precipitation, but I didn't talk about it here. But your question is more on the attribution side. Yeah, so I think at least in the framing that I've shown you here, the attribution problem, it has not gone away. So the issue that you've had in the past with the patterns being similar between, say, aerosols and greenhouse gases, we haven't addressed that at all. So that problem's still here. However, we have used this method in a more recent paper by my former postdoc, Zach Labe, where we use single forcing simulations where it's just aerosols, just greenhouse gases, and a combination, and then use this method to extract patterns in those different data sets. So in that way, we're using the standard climate simulation suite as a normal attribution method would to identify, these different patterns, even when aerosols and greenhouse gases project onto each other.
Yeah, no, that was really interesting, and I spotted the same patterns that Philip did, and I wondered, I mean, obviously the network is trained on a model that will have its own biases, and I wondered, I couldn't quite unpick it seemed a little bit circular, the reasoning that you train a neural network on a model and then evaluate the model based on the neural network's response when you subtract the mean. You did this.
So no, that's where. Yeah, so that's where observations are essential. We're actually trying to understand, why did the network get the observations wrong, which did not go into training whatsoever.
Right.
And so that's why, otherwise, yes, it would be incredibly circular. Okay. So in this case, this is where it's really important that we've trained on the climate models without any observational information, other than what went into the, if you will, the creation of the climate models themselves. And then we're evaluating the observations and then asking, hey, why'd you get this wrong? Let's go back and use these techniques. Does that make more sense?
Yes, thank you. Yeah, okay. I missed the step of the observations. And so how much do you...
I can, before dig more into question, I realized we're new to the new platform here a little bit. I think we should have encouraged probably attendees that they couldn't put also questions in the neural network chat, but I'll let you keep going.
No, yeah, please do. If you have any questions, please put them into the chat. I was asking about the, oh, you're right. Yeah. So using these interpretability methods, I wondered how far you can trust them and how far, they require the skillful network, right? So the network at some point doesn't do so well. And so, where's that balance? And I'm interested, to see.
Yeah, so a big question is, first, there's so many explainability and interpretability methods out there. Which one do you use? Right. The first answer to that is I don't think people know. So we actually have in our group a postdoc, Antonios Mamalakis, who has spent the last 2 years doing benchmarking of explainable AI methods for climate science problems to address this exact question. And especially to communicate, every method has its issues, nothing's perfect. What are those issues so that the tool users, if you will, know what they're getting into? I think that's the first question. And the second question I've gotten this question a lot, which is, well, what if your neural network's not perfect? How can you use these? And actually, we're not asking if the neural network's perfect, how did you come to your decision? The neural network can also be imperfect, and we can explore why it's getting it wrong. So to me, these XAI methods are really about understanding the network's decision-making process, even when it's wrong, which can actually be useful. What that means, though, is you cannot depend on these explainable AI methods to tell you the causality, right? They're not going to solve all the problems for you. So something that makes people, I think, a little frustrated is that you still have to know about the climate system to use these tools. And maybe fortunately, unfortunately, it's good for me. I have a job. But yeah, that we can't, at least the way we're using it, we are not taking the scientists out of it. It's actually, if you will, step one of many that are required to really get back to causality and physics and what's going on.
It's interesting you prompted my follow-up on causality, but you showed some work where you broke the response into clusters. Were they independent clusters, or are they
were?
And how do you test the independence?
So in that case, they were largely independent, and the way we tested that is just by going back through and looking, if you will, from a case-by-case basis of when one pattern was useful for predictions, the others really weren't present, etc. That's actually where I think out of all of this work I see the most promise is this concept of, up until now, most climate science has relied on linear methods, which sort of would smoosh all of those different pathways together. And if anything, this is just helping us pull them apart a little better than the old-fashioned way of having a graduate student print out 1,000 maps and stare at them for a few weeks. So I really think that's really an exciting application here.
Yeah. Can I come back to your last topic, which I found very interesting, the detection of change in the Lancet data. What I didn't fully grasp was the difference between the detection of change and then the attribution to human bits. You mentioned it finds sort of the road patterns, but have you worked on separating out sort of the change detection from the attribution to, say, roads? I mean, or could there be deforestation that doesn't involve roads and which could be still human? Yes.
So two parts to my answer. First, this is truly changed on anything human. And how do we know it's human for attribution? We are relying on all that work that Williams et al. Did with pieces of paper that they collected over years of what humans were actually doing. So one thing I'd like to really stress is we could not have done this without all of the work that was done without AI, if you will, beforehand. Because of that, we are confident that this is human, it's learning human-induced changes. With that said, what'd you say?
You use the Williams data as a labeled data set of human.
Exactly. Yes, which is why we've sort of already done the attribution sort of is baked in. With that said, I don't want to, I could give a whole talk on this and go into how the paper looks at SDGs and how it can support that, blah, 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 which is really fun. But I will say this network's not perfect either. So I always have to, do my caveat. It gets very confused over rocky deserts. I could talk about that for a while. But so my example here of roads with deforestation was just my interpretation of that XAI. And absolutely, it's also picking up on that tree line as well, because that's part of what humans have done. It's not just the roads.
Great, thank you.
We have a question for the audience, which is great. Thanks for getting involved. So Marco Karugi asks whether whether it works, and I presume he's referring to the predicting the year from your maps, and whether you can do that kind of regionally or whether you need the full global map. And that's an interesting kind of question. He says it's a basic question, but actually I think it's quite an interesting question.
Yeah, this is not basic at all, Marco. This is a fantastic question. Yes, you can absolutely do this regionally. There's nothing special about the globe. If you will, the globe is the easiest problem. It's the most information, but you can start to focus in on particular regions. So we have a few papers now, for example, looking at extreme precipitation over the Americas, so North and South America. We have others looking at just general precipitation, just say along the mid-latitude. So you can start to slice and dice the globe and do the problem again. And why that's extra interesting is you can start to look at the timing of detection. How long did it take the network to figure out and identify that force change? And as you get to smaller regional scales, that becomes a harder and harder problem, mainly because the noise gets higher, even if the signal stays the same. So I think this is a great question, especially, again, if you're interested in things like extremes and regional pictures. Yeah.
Fantastic, brilliant. Just on that, I mean, when you bring in precipitation, obviously there are observational uncertainties as well. Do you account for those at all?
Yeah, so what we've done thus far is we've trained again with climate models only. So we're only incorporating the differences across climate models. And I will point out this becomes an issue because climate models do have similar biases that they share. So the network learns those biases rather than them canceling out. With that said, however, we can then apply that learned network to different sets of observations and ask, is there any consistency here? Does the network get anything right about the real world? And with precipitation, that's particularly tricky because our observational data sets are so different, but we still see that the network is learning something useful, again, about the real world. I think this is where, however, these tools being used to identify biases in the climate models may actually be more useful. Because we know they're there.
Fantastic. Thank you very much. We probably reached the end of the session now, but that was a great talk, really interesting. Philip, do you want to close us out?
Thank you for inviting me.
Actually, I'll stick in the very last question because it resonated so much when you said we have so much data that we can't explore and the community should really dig into it. I wonder if you had thoughts what the community should do about it. How do we really make the community adapt some of these methods and dig deeper in the data than we currently do?
Yikes, that is a huge topic. Okay, I think I'll give you my spiel though about the AI side. In terms of first, because secondly, the data side, I think first is just making the data available, public, but not just public, but easily accessible, right? Rather than having to go through a lot of hoops to get it, which thus those of us in climate science, you have to go get a new data product and you sigh heavily and know that the next 2 weeks of your life have been spoken for. So from the AI side, I think a lot of what we're doing in my group and other groups is education. Climate scientists have a background in understanding basic statistics, data, noise, how to deal with that, but they just don't have the confidence or the tools to go about using AI. And actually, one of my big messages when I give these talks to my community is, you sort of already know how to do this. Let me just teach you a little bit extra, or a little bit of that software. And so to me, that's critical. But secondly, what's really important is there have been a big push, I think, across geosciences to teach people AI methods in sort of short courses, which I think are wonderful. I'm not trying to say they're not, but oftentimes, at least to me, we need to back up and we need to start with basic statistics first, because so much of what can go wrong with AI actually fundamentally comes down to some of that basic understanding of data science. So to me, my big push moving forward is to ensure that data science as a topic, rather than just machine learning, is really what pushes the whole field forward.
Fantastic. I think that those are really good words to close with. Thanks a lot for your insights. That was fascinating. I should say thanks again to you, obviously. I should also add that as I mentioned in the beginning, we're kicking off again with a series on AI for climate science. The calendar is still filling up between now and sort of the end of the year. So stay tuned. There will be many more interesting talks to come, but at a slightly lower frequency than we kicked off. We won't go weekly, but we aim for roughly monthly-ish or so. But yeah, so stay tuned, and thanks to everyone for joining.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.